Boom. Green. Yep. Hello and welcome back to Calculus 1. The next section is on computing limits. We already seen two ways to compute limits. Graphical approach sometimes you can't win. There we go. And the chart table. The next one is going to be called analytic, which is actually kind of algebra way. So we cover this new way in 2.3. So the first two ways were covered in section 2.2. This one is your section 2.3. First of all, any limit under the sun can be computed using first two methods. The trick is that you might not be able to graph everything because A, you might not know how to graph, or B, too complicated. And also chart, which is table of values, might be too annoying to compute. Right? You have a huge expression and then you have to punch the calculator for 20 minutes to compute one, and then you realize you have to do another 5 points, right? So we want to try to see if we can solve limits using 3. Now, some of the limits could and should be computed by the first two ways. It's easier. And for most part, engineers look at the graph and just say immediately what's what. But in some cases, the analytic one is necessary. So here's the first very simple example done all three ways, obviously, and then we'll see what else we can do. So say you have limit of x plus 3 as x goes to 2. So that's the question. We can solve this using the first method by graphing it. So this is y-intercept is 3. We have a 45-degree line. And as we approach 2 from the left, we are approaching this point. As we approach 2 from the right, we are approaching the same point, and that point is at 5. So using the graphical method, we find that the limit of x plus 3 as x goes to 2 is 5. Same problem solved by chart. We'll have, we are figuring out number 2, right? So we will have 3 values, 1.9, 1.99, and 1.999, getting closer. On the other side, we have 2.1, 2.01, and 2.001. When you add 3 to each one of these, you get 4.9, 4.99, 4.999, or on this side 5.001, 5.01, and 5.1. So both of these point clearly towards number 5. So we claim limit is 5. The new way is to use algebra and arithmetic. And it goes like this: if there is nothing weird happening with the problem, no zeros in denominator and so on, you are technically allowed to plug the value in because the problem collapses to a basic problem from pre-calculus. So this will be 2 plus 3, which is 5. You clearly cannot do that for 1 over x squared because it will give you 1 over 0. But in this case, you can. So if you are able to just plug in a value and get the number, you are done automatically. So another example for something like this would be, what is the limit at x approaches pi over 2 for sine x? Well, sine x has nothing weird happening, right? It's just a happy function. It's a wave that goes from negative infinity to positive infinity, never having 0 in denominator because it doesn't have a denominator. Therefore, you can just compute this and you will get 1. The one that you can't do this for is the tangent, because tangent x has a vertical asymptote at pi over 2. In this case, we cannot plug in. So you will have to be careful. You should always check if this method works. You have the function, you have the value that it's approaching, immediately plug it in. If you get 0 in denominator or you get anything weird happening, that means that you cannot solve the problem by plugging value in. You have to do something else. But if you do get a value, you are done immediately. Remember, limit computes the y value. You compute the y value by plugging the number in. So if nothing weird is happening, you are done immediately. Now let me give you an example when weird stuff is happening. So say you have a limit as x goes to 2 of x divided by x minus 2. So if you try to plug in 2, you are going to get 2 over 0. Can you compute this? The answer is hell no. So what do I do in this case? Well, I have options. Option number 1 is the graph and a chart, right? Option number 2 would be, can I do anything using algebra? In this case, we cannot because factoring, rationalizing, all of these techniques don't work. So technically, we cannot solve this problem by plugging in, and we cannot solve this problem by using algebra. Therefore, we have to solve this problem by chart or a graph. Now, this kind of analysis and which method you are going to use will be there for you through constant practice. So this is not something that you just learn and memorize and you just go and say. I get to look after years of looking at this, look at it and I know. But you have to develop that sense through working out 5,000 exercises. So if I plug in 2, I will get 2 over 0. So we cannot plug in to solve the limit. So what do I do instead? Well, I can look at the graph, or I can use the chart. Most likely I would use the chart because this is extremely easy to compute. It's not a big deal. So we can use the chart on this problem to figure out what the limit is doing at 2. So we know our usual suspects over here. 1.9, 1.99, and 1.999. 2.001, 2.01, and 2.1. And now it's time for you to compute this. All right, so what do I have for the first 1.9? Negative 19.
Yep.
Negative 20. Is it negative 19 or negative 20?
I got the negative 19. Negative 19.
What's the next one?
Negative 199.
Okay, and what's the next one?
Negative 1,999.
So what do we see from this pattern?
Adding another 9.
It's getting fun.
So it's becoming what?
It's going down.
What?
What?
Yeah, so what is the, where is this going? From the left?
Oh, the negative.
Negative infinity, nice. Now what's happening on the other side? What do we have? What's the 2.1 number?
20.
How much?
20.
20
Yeah.
or 19?
21.
21? And how about next one? And the next one? So what's happening here? So what do we conclude? What do we conclude? Does not exist because, very good, does not exist because they don't match. One side goes to negative infinity, one side goes to positive infinity. They don't meet at the same number. Theorem.
Positive.
If they both positive infinity, the answer will be limit to positive infinity. Cool, right?
Yeah. Very cool. I like it. It looked worse. It looked worse.
No. Oh no.
It's gonna be great. I'm excited. You guys excited?
Okay. Let's take a look at so before we dive into algebra here, first let's take a look at properties of limits. Or they call it limit laws, whatever. Okay, so the first one is that the limit of the sum of two functions is the sum of two limits. Now this allows us to take independent limits for every term if you have a function that has multiple terms. Yes?
Can you say that like a word?
The limit of the sum is the sum of limits. Limit of the sum of two functions is the sum of limits. You have the same one for difference. Just as a minus. Constant multiple. So if you have a constant multiple, you can kick the constant in front of the limit, and just perform limit on the function.
Oh, yeah, yeah.
Product. Quotient. And you will have to be very careful with this one now. The product and quotient for limits work only for limits. They do not work for derivatives, and they do not work for integrals. Both limits, derivatives and integrals will have special formulas to deal with these situations. So these rules are only good for limits. 6 is the power rule. And the last one is factorial power. I don't know why is that separate, just power is a power, but whatever. I mean fractional, not factorial, fractional. So these are the rules for limits. So here are some examples. Let limit of f of x as x goes to, say, 5, let it be 3. And then limit of f of x, sorry, of g of x, different function, as x goes to 5, let's say, is negative 2. And limit x goes to 5 of h of x, let's say, is, I don't know, 7, whatever. So now the question is, what is the limit as x goes to 5 of f of x minus g of x to the 4th divided by f of x squared plus h of x? This is function composition technically, right? So what would you do here? Yep, you will replace each one. So you will break it in using the limit rules, and then you will replace the numbers for each of the limits. What happened?
Would it be the top one? It would be 3 minus -2. Right?
Negative 13 over 11?
No, just for the top part, f of x minus g of x to the fourth, it would be 3 minus negative 2 to the fourth.
Yes. So using the limit laws, each one of these will get its own limit. So we will have limit of f of x minus limit of g of x, everything to the fourth, divided by limit of f of x, everything squared, plus limit of h of x. And you just replace the values. So you have 3 minus negative 2 to the fourth, divided by 3 squared, plus 7, which is clearly negative 13 over 11. $16? Oh yeah, 9 plus, yeah. Negative 13 over 16.
You want us to write it, like, say on the text, just like that would be,
Well, I missed a lot of stuff. You also need to write these.
okay. And you would want that on the text.
I will answer that by I don't understand the question.
Yeah.
Notation is not there for decoration. Because people in China speak the same language. They speak English better than anyone of these. Or European. You what? They produce it there? Oh, me? No. All right, awesome. All right, here we go. This is going to be now a section with spicier examples, so pay attention. So what is the limit as x goes to 2 of x squared minus 6x plus 8 divided by x squared minus 4? The first response is to plug in the value and be done. However, 2 squared is? Minus 4 is? So we have 0 in denominator. Can we plug in? Nope. So I'm just going to write it here in blood. Cannot plug in. Because 0 in the denominator. So we cannot plug in. That means that we have to use something else. We could use a table, but that's going to be a lot of computing, which is the table. Factoring, very good. Look at these guys. This could probably be factored. So let's see what the factors are. The top is negative 4, negative 2. Okay, so x minus 4, x minus 2. And how about the denominator? Now what? Nice. Can you plug in now? Yeah, right. So we have 2 minus 4 divided by 2 plus 2, which is, right, clearly negative half. Just make sure you remove the glasses. Make sure you remove the glasses before the sheet. And make it crisp. All right. Great. So this problem was possible to solve by factoring. Great. How about this one? What now?
You have a 0 in the denominator.
I have 0 in the denominator. I cannot plug in. Great. What should we do? We could rationalize. Very good. How do we rationalize? Multiply by conjugate. Very good. I'm still asking a question like a 4-year-old. What do you mean rationalize? What do I do?
Get rid of the root.
Yeah, how? What?
Square.
I can't square. What does the meaning rationalize? And conjugate. Someone said conjugate. What does that mean?
The opposite sign. So it would be root x plus 2.
Multiply numerator and denominator by root x plus 2. Okay. Let's see what you get. Go. So if you multiplied, you should get this, and then these guys cancel. So what do you get at the end? Very good. So you didn't know when you divide by 0, you get a quarter? There you go. So I hope you already figured out that I did FOIL the numerator and did not FOIL the denominator, right? We all see that. But let's do something way cooler. Same problem. So we multiplied in the first attempt to solve the problem. So we foiled, right? What's the other F word that we can use to solve the problem differently? Factoring, good. So we can factor denominator. Root x minus 2, root x plus 2 if you factor denominator. Nice. You can factor anything. So, limit x goes to 4. We have root x minus 2 in the numerator. Denominator factors into this. There's your 1/4. Right? You can factor anything. Yeah.
How are you getting 4? So the top cancels out with the bottom. Then you're left with 1 on top.
Root x. You just put some 4 in for the x.
Oh, he's plugging that
Yeah.
4.
The square root of 4
2
2
plus 2.
Jesus.
Oh my god.
See, so you got
All right. So for not just this course, but all future courses, anything can be factored. If you have a minus b and you want to factor that, it's simply root a minus root b, root a plus root b. Fair? Next time someone, gets into your face trying to be too smart, ask them how much is root 7 minus root 5 times root 7 plus root 5. Right? It's one of those, what do you know situations. Ask them this. Psh, let's go. It's going to be 7 minus 5, right? So it's whatever numbers you come up in the minus parenthesis, that's the answer. So 7 minus 5 is 2. Let's see if we can find something spicier. Okay, here's the next one, guys. Limit h goes to 0. One over 5 plus h minus 1 over 5 divided by h. I'm going to put a star over here on this one. So what's the only thing you can do in this problem?
Solve the top.
Exactly. Combine fractions. Solve the top. Good. Go. Common denominator on 2 fractions. Get it. All right, so the common denominator is what? Very good. So 5 times 5 plus h. The numerator becomes 5 minus 5 minus h divided by h. These guys cancel. And then you can put over 1 if it's going to make it easier for you. So just a little bit of algebra here. But this is the most important problem we're doing. Minus h, 5h, 5 plus h. If you don't remember from algebra, two that are far apart multiply and go in the numerator, and two that are close by multiply and go into the denominator. And then these guys cancel, and we're done. Yes.
Same for the test. Are they going to be literally just the prompt and we solve it like this, or is it like more involved?
Well, this is it. I hope you're not disappointed.
Literally just like this.
I know, lame. All right, let's see what else. So you know you can use the chart at any point in time. You can use the graph if you can. I think we have one more concept in this lecture and we're done. Yep. So one thing left. It's called the Squeeze Theorem. And this one can be a little bit tricky, so pay attention on the way I build up to the point where you can actually use it. The theorem says it's not a major thing, so I'm not writing it in red. So assume the functions f of x, g of x, and h of x satisfy f of x is less or equal than g of x is less or equal than h of x. For all values of x near a except possibly at a. If limit x goes to a of f of x is the same as the limit x goes to a of h of x, so 2 at the ends, equals say L, then the limit of the one that it's squeezed in between, which is g of x, also has to be that L. It's a squeeze theorem. Think of a sandwich. You have a piece of bread, a piece of cheese, and a piece of bread. If you're allergic to cheese, put 2 slices. The cheese is squeezed between 2 pieces of bread, and wherever you take, right, to a location L, whenever you take the 2 pieces of bread, F and H, the G, which is squeezed in between, goes there as well. So you have this nasty function, g of x, which you cannot factor, which you cannot rationalize, which you cannot, you'll see how it looks like, let's say, sine of 1 over x squared, right? Good luck with that. So what do you do with it, right? Maybe you can sandwich that function between 2 functions that you could easily deal with. And then whatever those 2 functions that are above and beyond the nasty function, whatever their limits are, the one that is squeezed in between has to share the same limit. So I hope that makes sense. Now there's a great graphic in the textbook. I'll just say, so these 2, this would be your f of x and your h of x, the 2 pieces of bread, and here's the cheese in between. So you see, it's some kind of function that oscillates, right? This is that point of interest A. And you see that they all converge at that same point, so the limit value of the function has to have that value. So you are sandwiching a nasty function in between 2 easy functions, and because you can compute the limits on easy functions, the one that is sandwiched in between has to share the same limit, because limit is just a y value. Yes?
What do you do if the impossible function is the outlier, meaning the minimum or maximum function, where, like, if you were to swap the oscillating g of x with f or h of x?
Well, in that case, it's not this method, because it is your job to come up with f and h that are nice and work. So you cannot impact red g of x, the one that is squeezed. But the other ones, you can pick something that will hopefully work. Apparently Calc 2 is over there. So let's take a look at the example. Beautiful. I believe the book has only 2 or 3 problems on this, so try to do all of those. Limit x squared of sine 1 over x as x goes to 0. So how would you find this limit? Now, pay attention how I build it up. We are going to build up this from scratch. We start this by realizing that sine x is bounded by 1. That means that sine x is in between a -1 and +1. So I'm going to start this problem by writing the bound on sine 1 over x. Sine 1 over x is bounded between -1 and 1. Now, this comes from your pre-calculus class. You have to know that the most sine can give you is 1, and the least it can give you is -1. That is known as the range of the function. If you don't know that, clearly you can't do these problems. So we start from the bound. Then you compare this function to the original one, and you realize that x squared is missing. You are going to multiply x squared everywhere. And now we get at -x squared less equal than x squared sine 1 over x less than x squared. So we were able to sandwich our bad function in between two easy functions. You see how I build it up? So I started from the notion that sine is bounded, cosine is also bounded. You start from there, and then you keep multiplying and adding the stuff that it's still missing, looking back at the original function. So now, limit of negative x squared as x goes to 0 is 0. And the limit of positive x squared as x goes to 0 is 0. Well, the middle is squeezed between two zeros, so what is it? 0. So by Squeeze theorem, the one in the middle is 0. Now, you cannot make that argument in any other way. You might want to say, well, that's clear because it's 0 times whatever is going to be 0. No, we are going to see examples later on in chapter 4 where 0 times infinity gives you a quarter. Right? We already seen the example when we divided whatever it was, 2 divided by 0 and we got a quarter, right? So those kind of arguments don't fly in calculus, which is why we have proofs. And over here, you might say, 0 times whatever is 0, but that you just got lucky. Because this could be a quarter. And you will see those problems when we do a L'Hopital rule section. I believe L'Hopital rule is 4.7 or 4.8. 4.7, I believe, 4.7. So in chapter 4, we are going to see that. So now looking over here, if you pick 0, 1 over 0 is infinity and sine of infinity is 1, right? Well, the trick is to actually understand that sine of infinity is, we don't know what, but it's bounded by 1. So you actually should read this as 0 times 1, right? And that's why it's 0. But later, you're going to have 0 times infinity, which could be 0, could be infinity, but could also be 3/4, depending on which functions are in the game. So we'll have to be careful about those kind of things as we move along. So for the squeeze theorem, you start from the bound, you keep adding whatever it needs to be added to all three sides. This is called a three-sided inequality. You keep adding and multiplying whatever is needed to make the middle function look the same. And then you start working the limits on the outside to come up with the numbers. And that's it. Yes?
So it being sine 1 over x made no difference?
No, because this is the first thing you compute, and you get a number, and sine operates on that number. Sine as a function cannot return a value that is bigger than 1. So, to be honest with you, I don't care what kind of function I have buried within the sine. When I compute, it will give me some value on which sine will operate. So that's why the answers that you are getting outside of the sine will be between -1 and 1, regardless what's inside. Now, if it's in infinity, sine of infinity is not defined as a value. But there are also some other techniques going down the line, so we'll deal with that. Cool? Of course, cool. It's Calculus, right? All right. Well, that's it for this one. Take a short break. We have one more when you come back, so you have some homework to enjoy and stuff. When I go home bored and